Any other question you have? Some of you posed some questions on that too. Even if that's not your question, I still encourage all of you to keep a close eye on all the discussion threads we have. And after you have attempted solving those problems, having your solution side by side, check against the solution I have provided, and making sure you understand those. Even though it's open book, but let me make it clear to you. If you don't do any preparation, don't look at those problems, and you're only thinking about, oh, it's open book, I can refer to those problems and solution on the fly during the test and figure out what's going on. You are certainly welcome to do that, but I'm sure if you do that, you will run out of time. If it takes you 10 minutes to write a simple SQL query, there's nothing I can do to help you out. Does that make sense? So you do want to make sure you are good at solving those problems without looking at solution. And solution is really just a quick reference point. Like you look at it like 20 seconds, 10 seconds, that give you the hint what it is. That's what the open book is supposed to be. It's not like, oh, it's an open book, I can take 20 minutes to understand what's going on, come back, solve this problem. That will work if there's one problem on the midterm test. But unfortunately, that's not the case. Right? So don't misuse or misunderstand or mispredict what's gonna happen under this open book policy. Right?
How many questions can we expect?
That's a good question. Right? How many questions do you expect? Well, generally, I can tell you this: if you have done the homework solutions, if you have done all the homework problems yourself and you feel comfortable solving those, you should have no trouble in the given amount of time in the midterm test to solve it. In fact, you should be able to find yourself have 10-20 minutes left to do checking and all that. That being said, most likely you will have about 2 relational algebra queries to write, 2 SQL queries to write. Okay? That pretty much covers the scope of homework 1. For the scope of homework 2, I'm still debating about it, but maybe there's one problem on disk, buffer, one problem on files organization page, then one problem on indexing, query processing over those file structure and indexing structure. So that's kind of the scope I'm considering. Okay? And I will, so the lecture time is about what? It is with 1 hour 40 minutes. Without the lecture time? Hour 20. So I will make it hour 30, so 90 minutes for the midterm test. Meaning that we will start 10 minutes early on the day of the midterm test. That will give you 90 minutes to solve all the problems. Okay, I will make an official announcement on Canvas. You want to take a note on that for your calendar. So don't arrive late for 10 minutes. So basically, arrive 10 minutes earlier than the regular start time of our lecture time on that Tuesday. Okay? All right. Any more questions before I proceed? Okay. Cool. So, inserting this value, it's a data entry with a search key value equal to 8. We're trying to insert into this index. We'll assume that the record corresponds to this particular data entry had already been inserted to the underlying data file. So that's a separate process. We assume this has been taken care of. Now we are trying to insert the data entry correspond to that record being already inserted into the data file. So that's what's going on here. And for this particular VPAS tree, the number of entries you can fill in a given page is 4. Okay, clearly that's 4. So if you try to insert 8, what happens is it comes down to this page. So 1 IO to load the root page, 1 IO to load this page. So 2 IOs, you're done as the right leaf level page that this new data entry is supposed to go into. But you do not have space. So you have to split kind of like this, So what you do is you create a new page. So initially what you have and ignore the record ID associated with each data entry. I show only the search key value for the ease of illustration, right? So now we are trying to insert 8 to this with no space. So we create a new page that's empty but has capacity of 4. And we do a 2-3 split in this case. In general, you can do either a 2-3 or 3-2 split. Okay? It doesn't really matter which side you push one more entry to. Okay? So 2-3 split means 2 and 3 stay here, and the other 3 entries, including the new entry, will come to the right-hand side. That's what I mean by 2-3 split. If you were to do a 3-2 split, it kind of looks like that. Alright? Then you make an index entry out of it, just like what you did in the static case, which is the smallest search key value. In other words, the search key value of the first data entry on that page, and a pointer to it, meaning page ID of that new page. Note that this is a leaf level in the sense that this actually has a record ID point to some, some data file, point to some particular page, some particular record. So you cannot remove this value from the leaf level. So you have to do copy up of the search key value in the leaf level, because you do want to leave a representation in the leaf level in order to retrieve that record back. Okay, so copy out. Now you have to somehow index this new page. So this goes to that 14 and 16. Right? This stays the same. Nothing here. Now you need to index this new page in the higher level. Otherwise, the higher level has no knowledge of this, which means you have to take this entry and place that into, which is 13. So this was pointing up here. What else? 17, 24, and what's the last one? Someone? 30. So I gotta ignore the other guys. So that's what it looks like. All we are doing is to take this entry here and try to place that into this. Do we have space? We don't. So you split. You follow pretty much the same procedure. So it's kind of like a recursive step. However, with one subtle difference, as I mentioned toward the end of the last lecture, you do push up. So you split. 2-3 split. What happens? So 17, 24, 30 move over. And 6 and 13 is to stay. Do you follow me? So not only the values move over, but you move the entire data entry, right? So the pointers is move over as well. We're going to ignore 24 and 30. 17, that index entry, point to this particular page, which is 19, 20, and 22. Of course, there are more here. Does that make sense? Yes? Alright. Now, 13, so I'm going to this. 13 is going to move over to make a space for this new entry. So 13 comes here, and its pointer stays the same, which is to this page. And this new entry 6 come over, takes the spot, point to here. So this page is set. The leftmost pointer stays the same, everything is good. Any question on this? Yes or no? No? Now, this is also another special case where we are at the root level. Right? We split the root page. As a result of that, we need to create a new root page. And this is the new page we just used, so we need to make a copy of the smallest key and make an index entry out of it. and place that into this new root page, which is 17. So this entry just come over here. Yes? Now you notice one thing. At this level we do copy up. So 6 here, 6 here. But at the index level, we no longer need this 17 value here because for index page we have the leftmost pointer as a special case. So we can safely remove 17, the third key value of that index entry, and the pointer associated with that index entry now become the leftmost pointer of that page. So there's one more entry here. This simply becomes the leftmost pointer. So the pointer associated with that index entry 17 is left behind to become the leftmost pointer of that page. And 17 is push up. This is called push up. And finally, you add the leftmost pointer to index the old root page. That's what we got. So this pointer here was the pointer associated with that index entry 17 as the result of pushing up the value of 17. Okay? Any question on this? Alright. Now let's do deletion. Okay? That's the insertion. Now let's look at deletion. Deletion is pretty much the reverse of what we said. Okay. The only thing is in deletion, the most natural reaction to deletion is to you split for insertion, so you do merge for deletion. Is that right? So you merge. But before you merge, we are just talking about tax reform, right? Society is not working at Dupont Street, right? If somebody is not doing well or somebody is doing too well, you eliminate them as an outlier. You cannot do that in a society, right? What do? In society, how do you fix this? You redistribute the wealth. Right? If you're rich, seriously, no kidding. If you're rich, you tax them more. If you're poor, don't tax them. Right? So that's kind of the idea behind this. So before you try to eliminate an object, in the society case is a person, you cannot do that. Right? So in the context of Dupont Street, you deallocate that page. You can do that. It's just a page. It's not a human being. So deallocate that. If you're not doing well or if you're too well, then eliminate you. So before you do that, you do redistribution of quote-unquote wealth. What's the wealth in our context? Well, the number of entries you have. Does that make sense? The number of entries you have. And how do you decide? Just like in tax reform, fantastic. You're going to set up this tax bracket, 20%, 25%, 12%. This number, nobody has any problem with the number, but everybody has a problem where you draw the line. Does that make sense? I'm all for 100% tax if you tax income above $1 million. Of course, I'm saying that now. If one day I become rich, I will all for 100% tax if income is above $1 billion. It depends on where your butt sit at, right? Does that make sense? Yes or no? Follow me, right? So similarly to the B plus 3, we need to define what do you mean by rich, what do you mean by poor when you do redistribution, right? So if you look at how we do the split, 2-3 or 3-2 split, we are observing a simple principle, which is every single page must be at least 50% utilized. If you don't have that rule, obviously I can even do this. Right? Nothing wrong with that. Does that make sense? But I do enforce this rule for a reason. Because if your utilization ratio is too low, what's the problem? Can someone tell me? If you let a page to be super underutilized, as it goes below 50% utilization ratio, what happens? And what's the extreme case of that if you go down that path?
You're just going to have too many IOs because you're going to put
Yep.
pages.
You're going to have too many IOs because you're going to have too many pages at a given level, and the height tree becomes higher. Fundamentally, if your utilization is too low, your fan out will be reduced. And remember, the height tree is log f of n prime, which is the number of beef level pages. So if your utilization is too low, your fan out is going to be reduced. As a result, the height tree will go up. So your query costs become more expensive, more IOs. So that's the trade-off. That make sense? And in particular, in the extreme case, if you don't enforce this, I'm going to go all the way down to just one entry per page plus leftmost pointer. So my fan out effectively is 2. In that case, you degenerate to essentially a binary tree, but using a single page, a whole page to store a single entry. So you're taking binary tree as it is and place that onto disk. As we already analyzed several times, that's a really bad idea. That make sense? That's why we ask for at least 50% utilized. And you cannot go possibly beyond 100% utilized. That's obviously the maximum you can go. And for this, people introduce a notation to capture this. They call that the order of view tree. The order of view tree. The textbook uses a particular notation called D, small d, order of view tree. So 2D represents the maximum capacity of a page in terms of number of entries you can hold. So what this is saying is the order of the tree is at least D. It's a value between D and 2. Does that make sense? So the order of the tree is defined as 50% utilized and the capacity of that. So this is the order of view. And this is the maximum capacity. So it must be between D and 2D for any given page. With one exception, which is the root level page, which is totally understandable, because look at the example I just gave you. If it's a newly formed root page, you will have just one entry. So you have to make an exception for the root page. So other than the root page, every other page in your BPath tree must have a utilization ratio at least 50% or more. Cannot go below that. But we also said you don't want to fully utilize all your pages. If you do that, you end up with splitting all the time. A single insertion will cause split all the way up to the root. Because every level is fully utilized. That's obviously too expensive. So is there a magic number to balance the trade-off of the two? You see the argument? From a query efficiency point of view, you want F to be as large as possible if you don't consider insertion and deletion. But from a maintenance point of view, you want this to be as small as possible so you can accommodate new insertions without splitting. So there's a fight between the two, right? How do you balance the trade-off? Is there a magic number? Like, is there a magic threshold I set my tax bracket, everybody is happy? Democrat, Republican, Donald Trump, everybody is happy. Is there such a magic number? I can tell you, I don't know about the answer for BPath tree yet, but I can tell you the answer for the letter. No, there's no such magic number to make everybody happy. I can tell you that. Knowing US politics, I can tell you that for sure. I'm willing to bet $1 million for that if you disagree with me. Okay? Now, to the BPath tree example, but the good news is, that's why we do science, we don't do politics. For BPath tree, there is a magic number. And the magic number is 67%. You may wonder why 67%? It translates to about 2/3. Why is that? Why 2/3 works? Oh, that's actually a very deep question to answer. And that will take me probably 4 or 6 lectures to explain just that. The reason it's a deep question to answer is because you have to show, because there are billions of different insertion sequences given a B-class tree, right? Just like buffer replacement policy, we analyze the competitive ratio of different algorithms, and we say you have to look at all possible sequence of requests and how they affect your buffer replacement policy, the performance of your buffer replacement policy. Remember that discussion? Even with just 10 distinct page IDs or 100 distinct page IDs, with the 1,000 requests, you got 100 to the 1,000 raised to the power 1,000, many different possible permutations. And you need to analyze, for each case, what's the performance. It's a very complex problem, right? Similarly here, in order to show, this is the magic number that works, you basically have to look at all possible insertion sequences and see which particular number gave you the best performance on average. You average out all possible scenarios, you add up, divide by the number of possible scenarios you have, you look at the average cost. Does that make sense? That's the way to analyze this. Of course, if you go down that path, you will never finish analyzing this because you have billions of possible permutations. By the time this entire universe explodes, you still are busy doing your calculations. Does that make sense? So you have to have a really smart way of calculating that. Follow me? And that's particular quote-unquote smart way is really, really complicated, which I don't want to go down. So somebody proved this in the early 80s with the Turing Award winner. Andrew Yao proved this, that if you set to 67% utilization ratio, on average, this gives you the best performance. Balance of the insertion and splitting cost as well as the query performance. Okay, so that's kind of the idea. All right. That's why in commercial database systems, the default utilization, if you do a bar coding of the, I will talk about bar coding later on, they typically always bar code the B-class tree with 2/3 utilization ratio for all the pages. There's a reason for that. It's not a magic number somebody, just come up.
So I was just wondering, I guess, does that 2/3 ratio, so it doesn't depend on all, I don't know, if say you were using RAM or an SSD, which has a very different access model than a disk, does that 2/3 ratio still apply?
That's a very big, actually it doesn't really matter whether it's SSD or hard drive, because the assumption here for the analysis is I'm going to look at how many number of splits I'm going to do, how many pages I affect, and how many pages I need to load from my query. I basically do my cost model is total number of pages affected, or total number of pages accessed, given a random query sequence and insertion sequence, insertion and deletion class. And of course, there is an assumption on that, which is given my input domain, I may have different distributions for different sequences. I may have higher probability of querying 2, 3 all the time rather than querying anything beyond 20, for example. That would totally change your analysis. So the assumption there is uniform distribution for all possible sequences. Given that, if I reduce to the number of pages affected or accessed, what's the best ratio to use? Okay. Now, deleting from B-class tree. So as I explained, you want to do redistribution first and do merge. What do I mean by that? So let's say we delete. So that's the tree after the insertion of value 8. So we delete 19. That's easy because this page is still above that threshold, 50%. So nothing to be done. Now, if I delete 20, what happens? Now, this page becomes underutilized. We need to do something about it. In other words, somebody is below the poverty threshold, you cannot leave that person alone. Right? You have to do something about it. So what do? Well, what you do is you borrow entry from your neighboring node. So in this case, this sibling node has more than enough. What do I mean by more than enough? Well, 50 is the threshold, right? But, which is 2 in this case, but you have 3. So you can afford losing 1. You can afford losing 1. Right? Again, this is in the contact view tree, that's why people our pages are fine losing an entry, right? In real life, good luck. And if you tell a millionaire, say you have 2 million and you don't need the actual million, give me 1. Good luck with that. So here you can do this. So you take one entry and you take one entry from here and place this into this entry. That's what we call redistribution of data entries. So you end up with 20, 22, and 24. 22 and 24. Are you done? No, because of this, you need to update the index value on the level above. Instead of 24 now, it's 27. So you need to do that. That's the resulting tree. Okay? So far so good? Now, this is your unlucky day. Okay, you can do redistribution, right? So I'm gonna delete 22 for you. Right? I just keep deleting where you just redistribute. Eventually, you're gonna have no wealth to redistribute anymore. Right? So I delete 22. Now you were trying to redistribute from here, you will fail. Right? By the way, you may say, can I redistribute from here? In this case, you cannot because first of all, it's just on the border. Secondly, even if it is not, even if it's more than underutilized, you cannot. You can only do redistribution from your sibling node. Think about this as the state of Utah, this is the state of Denver. Yeah, you can do that. This is the state of Utah, this is Mexico. No, you cannot do that. It has to be under the same root. That make sense? Right? So sibling node is defined as nodes next to you on the left or right, but share the same parent. So at delete 22, you are out of luck. So you have to do what? You have to merge. You physically eliminate this page. You physically eliminate this page. When you merge, what happens? When you merge, you're gonna either deallocate this page or deallocate this page. Doesn't matter which way you do it. You put all the data entries from the 2 pages into 1. Suppose we deallocate this. So we move these 2 entries over here, 24, 27, 29. And we need to, because you deallocate this page, you need to delete this index entry altogether. So that becomes just 30, and the leftmost pointer to this page. So you delete that index entry altogether. But what's the problem then if you do that? That particular page is now underutilized. And you can try to do redistribution at this level. You said, wait a minute, you just said you cannot borrow from here, but now we're suppose that's the UN, United Nations. Now you can redistribute through beyond United Nations. Well, as far as I know, there are no human civilization on Mars yet. Right? So maybe they're the United Universe of Nations. Right? It will not happen, but now we don't. So beyond that, you are out of luck. But at least at this level, you can now redistribute between these 2 nodes. But unfortunately, this node has nothing to redistribute. It's just on the border, so you cannot redistribute. So the only way is to do what? To merge. The only tricky thing here is when you are merging these 2 nodes, you have to remember where they came from. They came from the split of the 2. And what do you do in the split? You push up a key value, right? So when we merge them back, what do? You have to pull that key back down. You have to pull 17 back down to this level because 17 was push up during the split operation. The merge is just a reverse of that. So when we merge, you have to pull it down. So we end up with this. That's underutilized. After the deletion, you cannot do redistribution at that level. So you pull 17 back down. When you pull down 17, you deleted this index entry, right? And you deleted this whole thing. That's the leftmost pointer left to this page. When you pull down 17, 17 together with this leftmost pointer form a index entry, which was, that index entry to begin with. Remember when we push up 17, this pointer, the leftmost pointer, was the pointer of that 17 index entry. We push up that. So now we just put it back down and merge them back to an index entry. So that's what happened. Okay? Any question on this? Now I'm going to give you another example where we can do key redistribution at this level, at the nation level. Think about this as states, these are nations. Suppose now we can do redistribution at this level. Okay. Of course, this is a different trick. I'm not continuing the example before. I modified the example, right? So I deleted, I merged it, that's what I got. Underutilized. Now I can do redistribution with this guy. And this nation is rich. I can do redistribution with this. So what do you do? Well, you say, okay, I move, let's say, you can move either 1 or 2 from here to here. Either choice is okay. The only tricky thing though is the redistribution at the leaf level is very easy, involving just the 2 pages at this level. Redistribution at this level is a little bit tricky because you do have to go through this. Because this was part of this level, it was push-up. So if you want to do redistribution, you have to go through this, including this guy as well. So what I mean is, if you push one entry to the right, instead of pushing 20 here, you should do 30 and 22. And you push 22 back to where it is, and push up 20. If you were to do 2 over here, you need to push 22 back to where it is, push 22 it is to this new page, and push up 17 to that page. So that's only tricky part of this. So suppose I push 2 over, that's what we get. Okay? It's kind of like, if you think about the UN example I gave you, the chair, there are always a nation chairing the United Nations, right? They rotate every month. I forgot the detail of that. They rotate every month or every few months. And you cannot say, okay, when we talk about the distribution of debts and wealth among all nations, the chair nation is spared. No, it is not spared. Even though you are chairing the whole thing, but you are still part of the discussion, right? That's kind of the idea about this. So when you do redistribution, you need to go through that. That's about it. Okay, there are some more examples. I will leave it for you to explore. Somebody had a question just now.
Yeah, I was wondering. So I guess so the worst case for a deletion on the B plus tree be? It seems like you could end up doing a full table scan potentially, depending on how, if like everything.
Well, not really. If you think about the worst case is you are affecting 2 pages per level all the way up to the root. So the worst case is just this, 2 of this.
Okay.
Right? You don't need to go beyond your neighboring node, essentially. So bar loading of B plus tree. So the idea here is the following. Suppose you have a large table, billions of records, Google, Microsoft, you have billions of records. And you want to build an index over it to speed up your query processing. Of course, you can use the dynamic insertion and deletion algorithm, in particular the dynamic insertion algorithm we just introduced. But what's the problem of that? Let me show you what the problem is. Imagine I have this sequence here. Let's say maybe 15. So I have this data entries with values from 1 to 15. My B plus tree, suppose my order is 2, so my max capacity is 4. So what do I do? I use the insertion algorithm. I start with a single loop page. 1, 2, 3, 4. Of course, with the record ID. Now, when you insert 5, what happens? You get a split. Suppose what we do 3, 4, 2, 2, 3 split. Right? Now you insert 6, 7, what's the problem? Split again. You see how this goes, right? What's the problem? Well, you end up with every single page 50% utilized. You know, if you keep doing the example, this will be 50 utilized at all. Does that make sense? You end up with a tree that's 50% utilized, and you end up with tons of split operation, which is super expensive if you have billions of records. That's why if you have large number of records to begin with, you never use the dynamic insertion and deletion algorithm to build your tree from scratch. You do something called barcoding. And the idea of barcoding is essentially the same as what we talked about before for the static version of this, which is ISAN. You basically load them level by level. And in the process of doing that, you can control the utilization ratio. You can have each page 100% utilized, or you can have it 50% utilized, or you can have 75% utilized, whatever you want to do. The idea is you simply group. You store your data to a deep level, then every so many go to a page, every so many go to a page, every so many go to a page. Then you make index entry for each page, do that at every level go up. Essentially the same as what we did before. And you can control how many goes to a page. In other words, you can control exactly the utilization ratio of each page. This is much more efficient than building a tree from scratch by insertion. Does that make sense? So that's what we call barcoding. And once you have the tree built, after that, you use the dynamic insertion and deletion to maintain your tree. So that's kind of the idea. Okay? Yes, comment. Alright, so that's the only thing left is I'm going to do a live demo of bpop3 in a database setting. So this is our class-wide database. And in particular, I have two tables called test1 and test2. So let me show you the schema of both. As you can tell, they are identical. What it does is I wrote a simple program that generates 5 million records. 5 million. Sounds a lot, but it's actually tiny, right? 5 million is nothing for Google and Microsoft and people like that. So I generate 5 million records to each table. Each table. Does that make sense? And each record has a unique identifier, a name, and a rating. Think about this as student or sailors. And rating is a value between 1 to 100. And name is just some random string value I generate. And I generate this using uniform distribution on the ratings field. Uniform distribution on the ratings field. So each rating value has roughly the same number of records, which is how much? So 50,000. Each rating has roughly, not exact, because uniform distribution is uniform, but doesn't mean exact distribution, right? So each rating value has about 50,000 records. Sounds good? What I'm gonna do is I'm gonna select a range of values. But before I do that, I want to show you what's the difference of the two tables are identical, by the way. They have the same data. The only difference is this is test 1. It's using ENOBB, by the way. Storage engine. Show test 2. The only difference, if you look at them, is for test 1, there's a bpop3 on the ratings. For test 2, That's the only difference of the two tables. Yes or no? Yes? So what I'm going to do, actually, so what do you expect this answer to be? Roughly 100,000. I'm selecting two values out of 100, so 2% selectivity. I'm selecting about 2% of the records. Right? Out of 5 million, so roughly about 100,000. Not exact 100,000 at this point, but close. I'm going to run the same query on test 2. See a difference, right? Do you? I see a difference. If you tell me you don't see a difference, this is kind of the question I asked you last time. Select star from student, select reading from student, ask how many see a difference. Only 3 of you said there's a difference. I'm not okay with that. I'm okay with you cannot see the significance of that difference. That's okay, that's a different story. But any reasonable person looking at this should tell me there is a difference. In fact, there is a huge difference, right? Okay. $37 times difference. If you think about this at Google or Amazon, right? I'm making $1 per query I serve, which is really moderate estimate. Moderate is even not the right word to use. They make more than $1 per query, right? But suppose that's the case, which means per second, using the first strategy, you can serve 37 times more customers per second than the second approach. Which means your profit is 37 times more than going with the second. If you make $1 million on the second approach, you make 37 million on the first approach. We are not in Cuba, right, where profit doesn't make a difference. We're in the US, so profit not even 37 times, $1 million versus 2. I bet if I ask any one of you, 1 million here, 2 million here, how many of you choose 2 million? Who will choose 1 million? You for sure? Are you kidding me? Okay. I don't think so. I go with 2 million for sure. I go with 1.1. I don't even go with 2. I go with 1.1 if I choose between 1 and 1.1. I have no trouble admitting that. Okay? So there is a difference, right? You have to admit this. There is a difference, right? That's why people spend so much time doing this stuff. Otherwise, who cares? Right? If there's no difference, what's the point? That being said, now let me show you some more experiments. Oh, disconnect. So the time for query 1 stays roughly the same. What I want to do is the following. So we have 5 million, right? So the ID starts from 1, roughly. I'm going to count the roughly same number of records. Let's say I count from ID less than this. That make sense? For test 1 and test 2. Okay. what do you notice? There's roughly no difference of the two queries. I mean, there is slight difference, but not a big difference. And they're both much more efficient than, at least for the test 2. Test 1 is roughly the same as the query on the reading, but for test 2, it's much more efficient than the query on the reading. Why is that? And this is because most commercial databases, by default, build a cluster index on the primary key field. In other words, even though we only see a bpos tree on the reading, but there is an index on the ID field by default. Most commercial databases just do that, unless you as database administrator explicitly tell the system to do things otherwise. So there is an implicit index on the ID on both tables. That's why if you do query on ID, both are roughly the same cost. Okay? And final comment I want to make is this particular query here is fast because in order to answer this, you only need to do sequential scan at the leaf level because your tree is built on the reading field. You don't have to go down to the data file to do linear scan over there. Because all you need to know is how many entries are between 90 and 93. You can answer this using the leaf level alone. Does that make sense? If you were to select records out of this, what I mean is this, okay? Does that make sense? So what I'm doing now, I'm selecting the records with these values. Secure file. Okay. This, nice. I may not be allowed to select to all. This. Okay. So I don't want to do this because printing to scatter out will make no difference of the two queries because the output cost will be dominating. Unfortunately, I cannot run this because the security setup on this server prevent me to dump results to a file. But what I want to argue is, if you were to do that, that experiment will be showing you that there will be roughly no difference of the two queries, whether using index or not. And in fact, the first approach with index could be more expensive than the second approach. Why is that? Because you have a cluster index on the ID, meaning that the index on the rating must be an unclustered index because records must be sorted by the ID, not by the ratings. Now, if you're using ratings to find those records, what you end up doing? You end up doing this. For each record, you are paying an I/O to retrieve that. That make sense? So having index doesn't necessarily the case that having an index is always beneficial to your query processing. It really depends on the particular case you're dealing with. Do you follow my discussion on this? All right, that's all I want to talk about bpos tree. Now let's back to the hashing. Hash function basics, that's where we were, okay, before we jump back to the discount index. Okay, so let me eliminate all this. So the difference between random IO and sequential IO is this is sequential IO. This is random IO. Okay. So human, we are really smart. We don't have to take any training to know sequential IO is always better than random IO. If you know a person doing this, let me know. I'm interested in knowing him or her. All right, so back to the design of a good hash function. So hash function basics is just a function as any other function. Take an input domain and map to an output domain. That's all you do. Any function defined like this. Take an input value, output to a. So your input is x, the domain values, and output is y. Hash function is any function that do the mapping. From a geometry point of view, you're basically designing a curve to map this over. This essentially is this. This is essentially this, where this value is b, and this tangent is a. In the general case, you basically have really, whatever curve. Of course, if you go with the general case, describing this curve becomes super expensive. If it's a generic arbitrary curve like this, the only way to describe this curve precisely is what? Is to remember the correspondence between. Does that make sense? So there is a trade-off, right? Yes, a general curve may give you the desirable property, but it's super expensive to use that general curve. Because to describe the curve probably has become more expensive than whatever that desirable property may bring to you. Right? So that's kind of the trade-off. So in our case, we have a universe U. We hash from this universe U to a domain of M. This means basically 1 to M. And the domain of U, as we argued multiple times, is simply this, is N, right? So this is essentially where N is much greater than M. You can also, then to be precise, consistent with my slide. Instead of using 1 to M, I'm going to use 0 to M minus 1. So collision does have, because of this, you're going to have collisions. You're going to have collisions, right? You're going to have collisions. So desirable property, we want to make sure there is small chance of collision, right? Because if you have a large chance of collision, what do you end up with? You end up with an long overflow chain bucket. Okay? And recall what we said is we have a family of hash functions. What's the example of family hash functions? We saw that in the linear hashing example, right? This is a family of hash functions. It's just a collection of hash functions. In fact, you can define a family of hash functions by collecting some random hash functions. But typically, people collect a set of hash functions that share some similar properties and call that a family. Right? For example, these guys share the property that you're essentially looking at the last 1 bit, last 2 bit, last 3 bits, and so on and so forth. So there's a regular pattern between these functions. Right? So what we're talking about here is a single single hash function is this, but I may have multiple hash functions giving you exactly the same mapping, basically multiple different curves. So I can have H1, H2, H3, so on and so forth, right? All, in general satisfy this particular property. So I'm going to form a family of hash functions called capital H. So my capital H is a set of hash functions. And each of them satisfy this mapping constraint. And note that for each hash function, given a hash function, the clearing is fixed. The clearing probability is fixed. There are no probability actually, because once you are given a hash function, there are no probability because it's a deterministic hash function. There's not even a space of randomness. Right? So in the context of a single hash function, talking about probability is making no sense. It's deterministic. That make sense? However, if I give you a family of hash functions, and you can make a random choice over this. So your random choice is over this. Meaning you select one hash function, and I'm going to look at this particular probability. Whenever you talk about probability, you have to define precisely what is the space of your choice, of your random choice. So my random choice is this. What that means is out of this family of hash function, I select one of them. The selection, this particular selection is random. You can make a random choice. So that's where the randomness comes into the picture. And I quantify this probability over the random choice you have made. Okay, that's what this particular math formula tells you. And we want this probability to be small. Meaning I have a family of hash function, you have the choice of selecting one. Think about this as a game. The game is, as we said before, you're on this side, us. This is, think about, rivalry. Utah and BYU. Okay? So you can think about you as the universe, the potential players they're gonna put on field on Saturday night to play against you. Let's say they have 100 players to select from. But you don't select all 100, right? How many football players do you have on field? 12 or more than that?
11.
Huh?
11.
11.
11 for each side.
11%.
So 22.
So it's 12. So you select 11 out of 100. But Utah, you don't know what BYU gonna do. All you know is they have 11 players. Selecting out of the 100, you know their list of players. So you see all the 100 players. But you don't know which 11 you're gonna select. That's the discussion we had last time, which is there is a fixed set S. The set is fixed, small is 11, and it's fixed. Meaning that BYU made their choice of the starting 11 players, but they don't reveal that list to you, but it's fixed. Once they made the choice, they cannot change that. They submit that to the league, Thursday. Like so 2 days before the game, you have to submit starting players, and you cannot make change after that. That's essentially the game we're playing. Now select a set S, which is a subset of this, where the size is. So in our example, this is the set of U. 100, in our example is, this is 100, in our example this is 11. But they made the choice, but it's fixed. The tricky thing is, Utah, on the other hand, you don't know which 11 players they choose. I mean, how many possible choices do they have? That's a huge number. That's a huge number, yeah? But the tricky part, but the important thing to note is, once they submit the 11 player names to the league, they can make no change. Before that time, you can do whatever you want, but once you make your choice, it's fixed. I just don't know which fixed choice you have made out of these many possible choices. But once you select, it's fixed. Okay? That's the setup. What I want to do is, this is from imagine this is like super strong barrier, you cannot see anything going on there. So you want to design a hash function such that I'm going to map these players to an index value. And the chance for any two players to map to the same index value is small. That's essentially the game we're trying to play. That make sense? And you want to design a hash function for it. Of course, you have many different choices on your hash function. And you randomly select one of them, and you are hoping the choice you made leads to small clearing probability. Does that make sense? Yes or no? Yes. Okay. All right. So that's essentially what we're doing. So ideally, I want, because my goal is to map those players to different index values. So what's the best case you can do? The best case is for your hash function output to be exactly n. For 11 players, I use 11 index values. And I have no clear. One goes to a spot. Does that make sense? But oftentimes, you may not be able to do that. That's a perfect hashing, right? Without knowing the players, this is extremely hard to do. You want to have some actual rooms for in case clearing happens, right? So typically, n is more than n, and we can, desirably, we want to say n is roughly in the order of n. You don't want to be much larger than that. In the extreme case, if n equal to capital N, you can always do this without clearing, right? Why? Because you can simply design your hash function to be this. No clear. Yeah? For example, you represent each p-value player using their full name. No clear. But if you represent each p-value player using their first name, it really depends on what the other coach do. If he or she happen to select 11 players with distinct first name, you're good to go. But if he or she predicts that's what you're going to do, he or she will select 11 players with the same first name. Then your game strategy is all confused. You say block Pat. Your offense coach, you block you. Right? You have to do this because Patrick, the coach, did this once, right? They were reading the lips of the other coach. So you block this, you say block Ted. You player will be confused. Which Ted are you talking about? You have 11 Ted. But if you have 11 distinct names blocking Ted, perfectly clear. Do you see the game we're playing? Yes or no? Okay. You need to understand this to be an offense coach coordinator or defense coach coordinator. All right, so that's kind of where we are. And as I explained before, a general hash function like that may do the trick for you, but you don't want to do this because it will be too expensive to describe the hash function itself. Does that make sense? For example, to describe this hash function versus describing this hash function. For this hash function, all I need is two values, A and B. For this hash function, I need how many values? Well, if it's x1 to y1, x2 to y2, you do this for all the n values, then this hash function needs n values. So you're looking at 2 versus n. Huge difference in terms of describing the hash function. So, but if you have a family of hash functions, how many bits at least you need to have to distinguish these hash functions? How many bits you need to have in order to distinguish these hash functions? Well, you need at least this many bits. Why that? Can somebody explain to me? You need to be able to count them, right? 1, 2, 3 until set of age. So you need at least this many bits. You need at least this many bits to distinguish these hash functions. Yeah? Right? Log 2 of set age. And it's at least this because this is only to distinguish them, and each hash function itself maybe 2 or 1. If it's 2, then that's exactly the number of bits you need, because 2 is a constant. I ignore that. That makes sense? If each hash function is ax plus b, for example, this is a1x plus b1, this is a2x plus, of course, different a and b values, right? You don't use the same a and b value, right? You end up with the same hash function. So the number of bits to store them is exactly this, because each hash function is just 2 values, which is constant, fine, some constant number of bytes. So big O notation all comes to this. But if each hash function is like this, then obviously it's way more bits than this is. Yeah? Yes or no? But it's at least this, because we need to be able to distinguish them at least, no matter how expensive each single hash function is. And finally, another desirable property is H is easy to compute. You cannot come back and tell me, oh, I have a super nice hash function that can tell you a map B by U player, no matter which 11 players they select, to each distinct index value. So you can, on the game day, instead of call, suppose there's a really long name. I know a friend, his name is Marius Hadjilafakirio. If in the game time you call, hey, block Marius Hadjilafakirio, good luck with that. These guys might have run down 20 yards for you already. You want to say block 1, block 2. Where 1 and 2 index different players. Does that make sense? What do they tell you? Easy to compute the hash function. What that means is, you gotta call block 1, block 2, but in the real time, in the game time, what you're doing is block hash of Mario's hero, open bracket that does not map to 3. Then you say, oh, block Mario's hero should be block 3. But if this hash of Mario's whatever take 10 minutes to calculate, this guy might have done 3 touchdowns already. Does that make sense? So easy to compute. Okay, that's another. I'm sure this NFL football coaches use hash all the time. They probably don't know this. They have code name for each game strategy they have. Bird, eagle, all means different things, I'm sure. That's hash. That's hashing. Does that make sense? So if you read the lips of the other coach, if you cannot decode the hash function, it's useless as well. So the other coach said block bird. What does that mean? Who is bird? Does that make sense? So given this, the time to look up an item, is what? Is simply the length of this list. Why? Because if you go back to the basic structure, our structure is after the hash, we have an array storing elements going into each array. If there are no clear perfect, each array element has only a single element. But because you may have clear, each of this might be a list. The list might be of different lengths, depending on how many clears happen on that particular element. If you want to look up a particular value x, you apply the hash function so that you know where this element goes into. That's constant time, because array give you random access time in constant time. Accessing A1, accessing A10 is the same cost. However, because of clear, the length of each list at each element is different. Now you have no choice but scanning that list at that element to figure out where x is, because there might be clear. So if there is a clear, let's say hx equals to hy equals to 2, so what happens is the list of this is x and y. So in order to find x, you have to spend a cost of 2. You may say, wait, it's just 1, right? Okay, I'm 3. From 2. You have to go down both to find x. Yes or no? Okay, so that's essentially some basic observations. Okay, basic observations. So one way to spread elements out nicely is to spread them out randomly. Why? Because that definitely gives you a uniform distribution in the output domain. Right? X come in, it can go to anywhere between 1 and n with equal probability. Y comes in, Y can go to 1 to n with equal probability. I guarantee you when you do this, you have uniform distribution in n. What does that mean? The length of each list at this arrays is roughly the same. You know, that's the best case we're looking for. You don't want to have a skewed distribution, meaning having a single bucket with long list. You want each bucket to be roughly the same length. So doing this will be fine, right? But what's the downside of this? Well, if you do this, placing them is fine, but retrieving them becomes impossible because you make a random choice. Unless you remember the random choice you made, but that's essentially becoming this curve. You remember where each goes. But each of this mapping is random, so I can do this, I can also draw something like this. So but remembering this is, unless you say I only care about placing them into Mars, where they are on Mars, I don't care. Go Mars, go Sun, go whatever. So where Ted goes, I don't know, somewhere in the universe. You cannot do that, right? But it's a uniform distribution. So this is a bad idea. This is a bad idea. And another bad news is for any deterministic hash function. Deterministic hash function means for the given x, in this, hx always equal to hx. You may say, what's the point of this? Hx isn't that supposed to be always hx? Well, not necessarily so, right? You can have a randomized hash function. What I mean? Let's say, I'm deciding where to put my key at in my house. I have a simple strategy. If it's sunny, I'm going to put my key on the first floor. If it's raining, I'm going to put my key on the second floor. You wonder why I want to do that? Just put your key on the first floor. Well, I just want to do that. And then at the end of the day, ask you, where is my key? Key is the same. It's the same x. Is it in the first floor or second floor? Well, that's a random choice. Because Mother Nature is random. It's not like one day it's sunny, next day it's raining, next day it's sunny, next day it's raining. It's random. Does that make sense? So where you place a key into, depending on some random seed. In my example, the random seed is weather of the day. So you may have randomized hash function. So we get rid of, in our discussion, we don't consider randomized. Randomized hash function is actually a fascinating topic. I don't want to go into it, but it's really, really deep and really, really interesting. But we have to limit our scope, right? So we focus on deterministic hash function. But we do have a random choice. Don't be confused. We still have a random choice, even in the context of deterministic hash function, because we have a family of deterministic hash functions. Each of them is deterministic, but I do have a choice of which one to use. Does that make sense? Yes or no? Okay. So the value is for any one single deterministic hash function h, meaning to hash family is just one. You use just a single deterministic hash function. If that's what you do. And if the set of the universe is greater than this, there exists a set S of n atoms that all hash to the same location. Meaning the BYU coach must have a strategy of selecting 11 players, all 11 players go into the same bucket. No matter what hash function you use, if you use a single hash function, a single determinate hash function. Can someone prove this argument for me? Huh? Someone prove this argument for me. So let me repeat the setup. Then I will ask all of you to think about this. Today is what? Thursday, right? So coming back on Tuesday, so there is plenty of football game on Saturday for you to figure out what's going on. One game not enough. Look at another game. Look at another game. Look at another game. And come back on Tuesday. I'm going to ask you this. Okay? Why and this? Okay? What's going on? What's the setup? The setup is I have a universe of football players, football team. I think like size is n. Right? There's n players. This coach select 11 players out of this. So n is example, right? So the number of choices, let's say n 100. So what it says is I'm having this many choice of the possible s. It's set s with 11 players, and I select one of them, small s. That's an element from this. Where each element, the capital S is a set. It's not a single element, it's a set of 11 elements. What I'm saying is, on this side, if Utah coach decide to use a single deterministic hash function, map to a set M brackets. I want to use code 1 to M to denote tat, denote might, whatever, so I can block 1, block 2, instead of say block Mario Tachila for hero. That make sense? Unfortunately, if that's true, meaning n is greater or equal than n minus 1 times m plus 1, using our calculation, suppose I'm going to use only 3 buckets to remember 11 players. Or let's say to be, give you a little bit more room, 5 buckets to remember this, to distinguish these players. If my n is greater, meaning, let's check. 100, n is 11 minus 1, so 10 minus 5 plus 1. So in this case, it's what? 51. So in this case, there is always a chance that BYU coach gonna select 11 players all end up in one bucket, a single bucket. What's the best case for you? The best case for you is roughly 2 players per bucket. 11 players go to 5 buckets, so roughly 2 players. So when I say block 1, it's Ted and Mike. It's kind of be Ted, Mike, and give me another name, John. That make sense? So either Ted or Mike. But if they have 100 players, there is a chance BYU coach will select 11 players using your hash function. No matter what hash function you are using, you make your random choice, A and B. Once you make your choice is fixed, there is a chance that there is 11, all 11 end up in one bucket. So when you say block 1, you play on the look at you. I have 11 guys to block. Which one are you talking about? That make sense? And another tricky part is this s, small s, is also fixed. The BYU coach made his selection. Don't reveal that to you, and he cannot make change to this name, to this list of names. So that's the game. And think about why that's the case. So if they have 11, if they have 100 players, this will happen. But if let's say they have 40 players to select, that 11 players, good news for you. You can make a really bad choice on your hash function. You guarantee all 11 players will not be mapped to the same bucket. That's kind of what it says. Okay? Prove this for me on Tuesday. Okay? All right, see you.